Welcome to This Explainer. Today, we're diving into something pretty wild. We are going to uncover the invisible, microscopic dangers lurking inside the welded metal structures that literally hold our modern world together. You know, we walk past massive steel beams and perfectly smooth metal joints every single day without a second thought. But today, we're going to look beneath that shiny surface to explore a hidden phenomenon called porosity.
I want you to ask yourself a slightly terrifying question. What actually happens when solid metal starts acting like Swiss cheese? Just imagine, for a moment, relying on the structural integrity of a towering steel bridge, or maybe the chassis of a high-speed car. On the outside, those metal joints look perfectly solid, right? Completely unbreakable. But inside, they could be absolutely riddled with tiny, invisible holes. So how does that happen? And more importantly, how much danger does that actually put us in?
All right, let's quickly go over our roadmap for today. We're going to cover 1. The hidden welding threat. 2. What weld porosity actually is. 3. How it weakens joints. 4. The root causes of that trapped gas. And finally, 5. Prevention and repair.
Okay, let's jump right into Section 1, the hidden welding threat. Look, we've got to shatter this illusion right now that a smooth-looking weld is automatically a strong one. As our source material clearly lays out, quote, the trapped gases create a bubble-filled weld that becomes weak and can with time collapse. That is a pretty profound realization. Discontinuities like trapped gases can take what is supposed to be an unbreakable atomic bond and turn it into a massive structural liability. When stress is applied over time, what looks like solid steel can just suddenly give way.
Moving right along to Section 2, what is weld porosity?
So if we get right down to the microscopic level, porosity is basically just cavities formed when gas gets released from the molten weld pool. As the intense, blistering heat of the welding arc passes by, the liquid metal rapidly cools and freezes in place. And if gases happen to get trapped inside during that super-fast solidification process, well, they create these exact pinholes and bubbles.
But out in the real world, things get messy. On the left here, you have these nasty surface-breaking pores, which, by the way, are usually a giant red flag that there is massive porosity lurking underneath. And on the right, you've got what's called a crater pipe. This is a really specific type of cavity that forms when the welding arc is turned off way too fast, causing the metal to violently shrink as it goes from a liquid to a solid.
That brings us to Section 3, how porosity weakens joints.
The absolute crucial thing to understand here is that these gas pockets aren't just harmless empty space. They actually act as internal stress concentrators. By literally displacing the solid, load-bearing material, they drastically decrease the overall strength of the weld. So when a heavy load or even just normal vibration is applied to the metal, those tiny voids act as weak points where cracks can easily start and then spread, ultimately leading to total failure. Plus, if those pores manage to reach the surface, they create these perfect little pockets for moisture and chemicals to pool up, which kicks off creeping corrosion over time.
All right, Section 4, root causes of gas.
If trapped gas is our main enemy here, we really need to know where nitrogen, oxygen, and hydrogen are actually coming from during the process. Just look at this number, 1%. Think about the utter absurdity of a 1% margin of error on a chaotic, massive construction site. Nitrogen and oxygen absorption usually kicks off from poor gas shielding around the arc. If you get as little as 1% air entrainment in the shielding gas from, say, a tiny draft or a tiny leak in the line, it's going to cause distributed porosity. And if that air contamination creeps up just over 1.5%, you are guaranteed to get gross, completely unacceptable surface-breaking pores. The margin for error is virtually zero.
But hey, it's not just the surrounding air causing problems. Environmental contaminants are huge culprits too. Hydrogen, for instance, loves to sneak into the molten pool through invisible moisture on welding electrodes that just weren't dried properly. On top of that, if a fabricator decides to weld right over surface rust, grease, oil, or really thick primer paint, all of that material instantly vaporizes under the intense heat. That generates a massive amount of trapped fumes that literally have nowhere else to go but straight into the metal.
We also have to think about the physical shape of the metal itself. Geometry can literally be a trap here. The risk of trapping this gas is way higher in structural T-joints compared to your standard flat butt joints. When you're fillet welding a T-joint, especially if you're hitting both sides of that vertical piece, you are essentially creating a really tight crevice. And that crevice acts as a natural trap for all that excessive gas bubbling up from surface contamination or oversprayed paint.
Let's wrap things up with Section 5, prevention and repair.
Figuring out how to prevent this means matching specific construction materials to their most threatening gases. And honestly, it's a completely exacting science. Just notice how carbon-manganese steel is threatened by all three major gases, which means you have to do some really heavy grinding just to get the scale off. Aluminum, on the other hand, is wildly susceptible to hydrogen, so it requires an intense chemical clean, then wire brushing, then degreasing, and scraping. It is an incredibly meticulous prep process before an arc is ever even struck. So what are the actionable, precise steps welders actually take on the shop floor to stop this gas generation? First off, completely clean the joint of any rust, grease, or moisture. No exceptions. Second, use totally dry electrodes and dial in that shielding gas flow so it's not too high but not too low. Third, the welder has to maintain the perfect arc distance and actually reduce their travel speed just a bit. Slowing down the arc just lets that molten pool stay liquid for a fraction of a second longer, which gives those trapped gases the crucial time they need to bubble up and escape to the surface. Finally, make absolutely sure any weldable primer is strictly kept below the manufacturer's maximum thickness, usually around 20 micrometers.
But okay, what happens after the weld is totally done and cooled down? How do we check the work? Well, while surface pores are easy to spot visually or with magnetic particle testing, finding that hidden subsurface Swiss cheese we talked about requires some serious high technology. Inspectors have to break out advanced X-ray radiography or high-frequency ultrasonic sound waves to literally look straight through the solid steel and spot any dangerous voids hiding inside. And if they do find unacceptable porosity, well, there are absolutely no shortcuts. You can't just paint over it and hope for the best. The defective portion has to be aggressively removed. Welders will get in there and grind it out, or use carbon arc gouging, which is essentially melting and blasting the bad metal completely away until the defect is totally gone and you're left with a clean groove. Then, they have to re-weld the entire joint perfectly to spec. And if the porosity is spread all over the place, the whole weld gets scrapped and completely redone. That's the only way to guarantee the structure's strength is restored.
So I'm going to leave you with this thought. The next time you're driving over a massive steel bridge or cruising down the highway in a fast-moving car, are you going to wonder what microscopic chemical interactions and potential invisible voids might be hiding inside those seemingly unbreakable metal joints? It really is a stark reminder of the invisible, high-stakes physics that hold our entire built environment together. Thank you so much for joining me on this explainer. I can pretty much guarantee you'll never look at a metal joint the exact same way again.